I'd like us to focus on two questions, both of which you have a provocative response to. One is inspirational, the second is philosophical. The philosophical one is, what is math? The inspirational one is, why do you believe that IQ, which is traditionally thought of as a necessary component to doing math well, why do you think that's overstated when it comes to understanding or contributing to breakthroughs? Let's tackle the conceptual ground first and get into how fear holds people back and practical steps later. What is math?
That's a very difficult question. That's a question that is officially too difficult in the sense that nobody seems to agree on the definition. And it's so I have in one of my Substack posts, I have a screenshot of Wikipedia for a couple of months ago. It's been reshuffled, but the screenshot, the content stayed the same. The definition of mathematics, according to Wikipedia, says that nobody is agreeing on the definition of mathematics, which is a big issue. You know, you're teaching something to billions of people, and you don't really know what this is. So I think people have been mistaken because they were trying to define mathematics without any reference to human beings. So there are two ways of doing that. One way is to say that math is about, it's a science of numbers, of shapes, of things that exist in the Platonician world of ideas. And there is the other approach that is to say that, math is about logic, about proving things, about having axioms, theorems, and all that. Now, it seems like this is correct from far away, but when you practice math, you realize that there is an issue with both definitions. Basically, these objects that exist, well, it's not really clear what this means. It's one of the few scientific areas where people still refer to things that we cannot touch. They are very abstract, so nobody seems to agree whether these things make any sense. And the fact that it's about proof is actually something that's really contradicted by the practice of math. You spend your time dreaming, daydreaming, coming with crazy ideas, testing your intuition. So my definition of math, but it's mine, it's not an official one, would be that it's a special technique that involves imagining things and pretending they really exist, and pretending they have properties that are absolutely true. And this thing is gradually changing your intuition and make you believe that these things actually exist. So the Platonician side, which is that you believe that these things are really existing, is a side effect of math. And the logic side is the core technique to produce that side effect.
When you say that we don't know what we're observing, we can't observe math, we can't touch math, even physically speaking, you're not touching the objects because there's some barrier between you. It looks like there's direct contact here, but you never actually have direct contact if you zoom into the atoms and so forth. So what is it precisely that you mean that we don't touch math?
Well, what you can touch is, you can touch the practice of math. You can touch someone who is doing math, and you can discuss with someone who is doing math. And yourself, you can do math in your brain. So my favorite example of that is, can you imagine a circle? Can you?
Mm-hmm.
Can you see it? Can you touch it? Can you make it bigger and smaller? So, this is a very simple experiment that shows that there is something really weird going on in your brain. You feel that you see something, but this thing is not really there. So you sense that you can touch it, but of course it's not a physical object somewhere. And its properties, being infinitely thin, being perfectly round, these things do not exist in real life. So what is going on in your brain when you do that? So if we stop doing metaphysics for a while, and we forget about the traditional way of thinking about this question, which is, yes, circle exists in a kind of Platonician way, but if we just focus on what is really going on, well, there is you with your brain doing stuff in your brain, and this stuff seems to have some effect on your brain and do weird things in your brain. What is this activity? How do you characterize it? This thing, for sure, it exists. I mean, this is a true activity. It's a physical one. And so there is that article that I absolutely love, and I think that anybody interested in this question should read it. It's a paper by Bill Thurston, the great geometer, and I think it's from '94. It's called "On Proof and Progress in Mathematics," and he comes up with that stupidly circular definition of mathematics, saying that mathematics is what mathematicians do. But I think he's right in a very profound way. That is, probably the best way to understand mathematics is to deflate the ontology, to stop trying to do crazy metaphysics that we don't really understand. Just focus on what we are really doing. What are we really doing when we do math? And this is quite interesting.
There must be some through line, though, because I imagine if in 200 years from now, mathematicians or people who call themselves mathematicians all of a sudden are working on installing power lines and building homes, for some reason it evolved to that. We would say you're no longer practicing. You're using the same word, but the word has changed and you're not referring to the same object in a sense that people were referring to back then.
You're completely right. And the actual definition by Thurston from this article, I think there is a seed in it that is, it contains the study of numbers and of shapes, So you start with what we agree on being mathematical objects, even though we cannot really define them. But what we can do is we can define the fact that we're thinking about problems with numbers and shapes, because these things we're familiar with. So of course, yeah, it has to include arithmetic, it has to include basic geometry. And then there's a bunch of other stuff coming with that. And this is the activity called mathematics. And Thurston even says that the job of a mathematician is to try to improve the understanding of mathematics by human, in the sense that we don't get a quite perfect understanding of these things, but we try to make sense of them, we try to understand them, we try to study them. And doing that, we do a bunch of things. And this is this entire field that we call mathematics.
So when a mathematician is thinking about circles and spheres and so forth, these are, let's call them the objects of math. And then there's the practice of math, publishing papers, speaking to people, a community. In physics, it's similar in that you have a model of an electron, but the difference is that we think the electron is something out there. Now, in math, what are you modeling?
So this is the question. We don't really know. I don't understand physics, to be completely honest with you. So it's not a perfect comparison point for me, because I always struggle with what is an electron. I've never seen one. But at least in mathematics, you define the stuff you're working on. So you give a definition. And that definition is basically playing Lego with objects that you already agree that are existing. So the standard way to play Lego nowadays is to start with sets, even though we don't really know what is a set, but we have a fairly stable, naive intuition of what is a set, and from that we can build more and more complicated objects. So in a way, the formal side of mathematics is basically the construction game that you're playing when you do math. But what's interesting is if you study logic and formal logic and formal mathematics, you have to accept at some point that what is true is formal statements that have absolutely no meaning, in a sense. So there is a dissociation between the activity of mechanical proof and the activity of meaning making. And when you do math, you actually try to align the two things. And this is what makes math interesting. So I think that these two aspects of mathematics are equally important. And actually, mathematics is this back and forth between having a meaningless definition, but it's just a syntactic game of combining axioms and deductions, and extrapolating meaning. And meaning is a human phenomenon. And this is where you cannot really eliminate the human in the mathematical practice. Even if you can formalize proofs, the fact that the proof is a proof of a theorem that has a meaning is what matters to you.
Okay, so just 2 minutes ago or so, you mentioned something about Lego, and we assume that these objects exist. But then it sounded like you were saying, well, these are just also the rules that we agree on, almost like chess. No one would say that the rules of chess exist outside of, or that they're referring to something that exists. I mean, the rules of chess exist, but what I want to know is, what is this alignment of a human notion of meaning making, and then the chicken scratch that is just something that we agree, you have these symbols here, and then you can manipulate it in so-and-so, and A can imply B, and so if you have A, then you could infer B and say B is true. So Help me understand that, because when people say, well, this is a human enterprise, there's the tendency to think, well, then it's arbitrary.
And it's a tendency that is very profoundly ingrained in our culture, but is wrong. It's not because it's a human enterprise that it's arbitrary. And it's not at all about social deconstructivism of mathematics. It's not at all about that. It's just about acknowledging that there is something in mathematics that cannot be explained by formal logic and can only make sense if you view mathematics as a cognitive theory, as a cognitive practice. So, so let's pretend for a moment that we endorse the formalist view on mathematics. That is that, mathematics is just a meaningless game of symbols, and these things, because they're not human, because they're very stable, because they're machine provable, they survive humans, and they're kind of eternal in their own way, and there's no human involved in doing that. Now, the problem is when you look at how the formal theory of mathematics is built, you start from the axioms of, let's say, Zermelo-Fraenkel. But why do you choose that? What do they mean? Why do you study this set of axioms? So if you open a book about set theory, that's an interesting thing. And actually, this is really what got me into that story. Some while ago, I was teaching a class on the foundation of mathematics. And I was trying to do what I always did when I was teaching mathematics first, try to define the objects. And I realized something that I knew, but I had not fully realized before. That in set theory, when you say for all x, you don't say for all x a set, you say for all x. And when you have the axioms, let's say the axiom of extensionality that says that for all x, for all y, blah, blah, blah. X and y do not refer to anything. And actually, for all doesn't mean for all. It's just a symbol. So you have a set of strings to which, if you stick to the formal theory, are absolutely meaningless. This is already annoying. Why would you study that? Well, because apparently it seems to be consistent, even though we cannot prove it. Well, it's not a good reason. There are many sets of axioms that are consistent that we do not study. We study it because we attach meaning to that. And meaning is a cognitive phenomenon. It's not in theory. There is nowhere in Zermelo-Fraenkel theory an explanation of what a set is supposed to be. And the word set only appears on the book cover. It's never mentioned inside. There's no description of what is a set. There's no properties of set. They're just statements that are just meaningless. Now, you could say, okay, we project meaning, but this is an optional thing we do. But this is not the case either. And actually, I think there is a very strong technical argument for that, which is the way mathematics behave as a scientific field. If it was a meaningless game of syntax, if we were to introduce a bug in the system would collapse. If you have a math paper, they're never really written in the full formal way. They have human hand waving blended with formalism. This is the way math papers are written. But sometimes, because of that, there is a bug in a math paper. There is a theorem that is not true. And there are other papers citing that paper. And they use a theorem that is not true to prove other theorems, and can go on for 50 years. It happens. It happened in the past that this thing went on for 50 years without anyone noticing there was a bug. Now, if it was purely a formal theory, there would be absolutely no reason why mathematics would not collapse from that. When Andrew Wiles came up with his proof of Fermat's last theorem, the first proof he came up with was wrong. And then he fixed it. But if it's just, assembling something that has no meaning, there would be no reason why a false proof could be fixed. What does it mean to fix a proof? Every mathematician agrees that, this is what Wiles did. He had a proof with a bug, and then he found a fix to his bug. So if you want to make sense of just this very simple objective event that happened in the history of mathematics, you have to agree that there is meaning, because if there's no meaning, there's no way to fix a theorem. Fixing a theorem is coming up with a theorem that is close to the one you thought was correct. Or maybe having a lemma that is close to a lemma that you use that is wrong, but maybe there's a lemma that's close to it that is correct. But being close to is absolutely impossible to define in the pure formal approach to mathematics. It's not that it's incorrect. It's not that it's an incorrect notion. It's a meaningless notion. You have no proximity between two formal statements that have no meaning.
There must be some survivorship bias here, because I imagine that there's a variety of theorems for which someone said, oh, all we need to do is fix this. We found an error or a bug or what have you. And then in the process of attempting to fix it, you realize the theorem was false. And the ones that have survived, we say, well, that points to evidence that we as people are capturing something that the formal systems have not yet caught up to. Do you also see that or no?
Actually, strikingly not. I mean, of course, you will always find examples of proofs that are wrong. It's just flat out wrong. This happens, And probably the proof that Fermat had in mind when he said, I have a very beautiful proof that is too long for the margin. Probably this proof was unfixable. That's good. We have good reason to do that. But to think that. But if you look at the published literature that is full of bugs, it's very rare that these bugs are unfixable. And it's very rare that the consequences are really destructive. Yeah, of course, maybe a bunch of papers are citing this paper and they're citing a lemma that is not valid the way it's used, but you know what? It doesn't propagate usually. So there's something really strong about, and I think it has to do with the fact that it's done by humans. I think if it was a machine, trying to greedily learn and prove things, it would lead to disastrous consequences. But human beings, they write math papers when they understand what they're talking about. So that's why actually they don't lose their sleep. We all know that the papers we publish are full of bugs, but that's okay because the bugs are fixable.
Wouldn't the Platonists just say, look, I have a simpler explanation. Fermat's last theorem is true because it exists. It's true. It's just our description of it was false, or our description of the proof of it was false.
Okay, so you this is Platonician view. This is Platonism. You pretend that there is something that is the canonical theorem that we're discussing, and this thing could have had an error of transcription when we wrote it down. That could be about the statement, that could be about the proof. Now, this idea that these things exist is very close to what I'm talking about, except that I don't think that we have to assume that this thing exists ontologically to agree that they exist in our intuition. There is another example of that. That is a more recent example. That is, there is a team with Kevin Buzzard who was trying to formalize the proof of Fermat's last theorem. And they started the project, I think, about 18 months ago. And in a few months into the project, they run into an issue with one technical theory they were using that's called crystalline cohomology. That is a very technical thing invented by Grothendieck and one of his students. And they found a bug in a lemma that's been used for, I don't know, many years, but for a very long time. That goes back to the foundational paper of crystalline cohomology. And they realized that actually the lemma was wrong. So in a sense, and that's interesting, there's a blog post by Kevin Buzzard describing his feeling. He being a formalist, officially a formalist, he says that, the minute we realized that this lemma was false, the whole theory of crystalline cohomology collapsed, vanished, disappeared, disintegrated into nothingness. And, well, that would be the official formalist standpoint. But on the other hand, he says that in his head, he knew that it was fixable because he knew that crystalline cohomology had been used for maybe 30, 40 years without, people running into issues. And he says that, if there was a massive bug in the theory, and if the theory had really no reason to exist because it was flawed, then we would not have been able to use it without running into issue for 50 years. And this is, so you can interpret that, as you suggested, as the idea that there is somewhere a theory that's called crystalline cohomology that exists in a kind of perfect world. But there is a different explanation, which I think is more interesting and probably more modern in its approach. That is to say that when we understand crystalline cohomology, what does it mean for a human to understand something? It means to align a number of mental representations of the thing we're talking about, but also other things for our past experience and trying to articulate that into a coherent worldview. And this is, I'm really talking about a neural phenomenon. I'm not talking about some magical stuff. I'm not spiritualist. I'm just describing that, in your brain, this thing makes sense and it's coherent and it's meaningful and it gives you a very pleasant feeling of harmony, which is, again, a physical phenomenon. It's not a magical one. You feel that things are in place. Well, this thing says something about the theory. There is that formal layer at the bottom, and you're kind of building that meaning on top of that. And so what is mathematics? If you look at it from this perspective, it's a very unique technique of relying on what I call the game of truth. The game of truth is pretending that you can write statements that are absolutely true and you can make definitions that are absolutely rigorous and you can play Lego with that and make formal deduction of new things that will be absolutely true, which things that, when you talk about normal language, this never happens like that in real life. Language does not behave like that. But when you do math, you pretend that there is that kind of alternate world of mathematics where this game of truth is describing reality of this alternate world. Now, when you do that, it has a certain effect on your brain. You're basically learning on a new set of synthetic images and ideas that you create playing that game. And this thing seems to have a very powerful effect on consolidating your intuition. And this is what makes you both happy and also probably a bit smarter when you understand some mathematical concept, because your worldview is kind of compacting and becoming more luminous in a way. And this is the actual phenomenon that is going on. It's a property of neurosystems exposed to that game of truth. And there is something that is working here. It's basically a machine learning theorem that says that should say, I don't know how to write it properly, but there should be a theorem that says when you play that game with a human brain, and probably with some sort of, you could play the same game with artificial intelligence probably, then it creates better representation that are very powerful and help you make sense of the world.
I remember the doubt before launching this podcast. What if no one listens? What if I'm wasting my time? If you've ever felt that way about starting a business, Shopify is the partner that turns uncertainty into momentum. They power millions of businesses and 10% of all US e-commerce, from Allbirds to Gymsharks to brands just getting started. No straggler left behind. Shopify's AI tool writes your product descriptions for you. It enhances your photography. It builds you a stunning store from hundreds of templates. Forget about the normative haze of bouncing between separate platforms. Shopify puts inventory payments and analytics under one roof with the propriety of a true commerce expert. Their award-winning 24/7 support means you're never alone. And that iconic purple Shop Pay button, it's the backbone of their checkout, the best converting on the planet, turning abandoned carts into actual sales. It's time to turn those what-ifs into with Shopify today. Sign up for your $1 per month trial at shopify.com shopify.com/toe. That's shopify.com/TOE. What's the name of this framework of yours or this worldview? So there's Platonism, which was referenced earlier about mathematical facts exist, they're just true, they're timeless. Then there's a formalism, which says that these mathematical facts are rules of a game. We could change the rules and we could equally explore arbitrary rules and they just don't correspond to something at some human level, but that's fine because we just decided that these rules are the ones we're going to explore. And what's the name of yours?
So I name it conceptualism, but I should put a disclaimer that I'm trying to articulate something that has been in the air for a while. So if you read Thurston's paper from 1994, you get these ideas, but they're not like pushed to the same degree of assertiveness because, of course, that was 30 years ago. If you go back to 1979, there is a beautiful paper by Ruben Hirsch that's called "Some Proposals for Reviving the Philosophy of Mathematics" that contains some of the same ideas. So it's not just my ideas; it's a train.
Mm-hmm.
It's a train that is, I think, in a way, in private conversation. Even though many mathematicians would call themselves Platonician, if you push them a little bit, they will say, okay, maybe this is what I mean. I mean, I perceive them as existing doesn't mean they really exist. Same thing for the people who call themselves formalists. When you push them, they agree that, like Kevin Buzzard said in his blog post, he said, okay, crystalline cohomology had disappeared, but in my mind, it was still there somewhere. So he agrees that there is an intuitive side to mathematics. So it's a latent consensus that I think is not everybody agrees with that, but I would say that a good chunk of the current mathematical community agrees with the core, maybe not with the summary, but with the core tenets of this way of framing it. So I call it conceptualism because I had to try I had to decide to put a name on it. And conceptualism refers to the debate on universal. That is a very interesting medieval debate. A story of William of Ockham and before him Abelard, and all these people run into trouble for basically challenging the dominant Platonician worldview. That I would say that our civilization is primarily believing that concepts are real things and they really exist. There was and there is still this opposite view that is, concepts, they don't really exist. It's just convention. That's called nominalism. You basically declare that everything is an arbitrary game of social convention. And conceptualism is some sort of middle ground, but it's not. Middle ground is usually a weak thing. It's a thing that because you don't want to fully agree with the two extremes, so you declare that you're in the middle. Actually, conceptualism says something that is additional to these things. It says that the abstractions that we're dealing when we do mathematics or when we describe the world, when you use the concept of an electron or things like that, they're not existing in reality, in external reality. They're not mere convention of language, but they are produced by our cognition, and they're byproducts of the way we structure our understanding of the world. So they exist in our brain. And I do think, that's my interpretation, but I know that some people might disagree with that, but I do think that the things we've been seeing with, the way neural networks, artificial neural networks work, it kind of validates the conceptualist approach that says, basically, when you pile up layers upon layers upon layers of neurons, then you will see that you would get higher and higher level of features that are generated by the different layers of these systems. And basically the neurons specialize on being excited when you encounter certain concepts. And this is really I would say, it's a conjectural interpretation. In the brain, it's not exactly one-on-one. It's not one neuron equal one concept, but there's something to it. And I think it's a good metaphorical summary to what is the conceptual standpoint. It says that our brain fabricates abstractions in the form of concepts.
How do we know when we found the right axiomatic system?
When we don't have issues with it. It's when how do you know that you have the right operating system for your software? Well, but you can have two problems. You can have one problem is you have a bug just doesn't work, it's broken, and you know that the first attempts to uh, formalize set theory ran into big issues, and Zermelo-Fraenkel solution was basically a fix of prior approaches to that. And the second thing that second issue you can have is there are things you want to express that you cannot express in this set of axioms. And actually, it's interesting to note that modern mathematicians, they kind of, everybody's kind of believing that we're using Zermelo-Fraenkel, but we do things that are not really fully within Zermelo-Fraenkel. I don't think that category theory is well captured by foundational set theory. I think it's. I don't know exactly how it works. To be honest, I'm a practitioner of category theory, even though I'm not completely sure that it's well founded from a logical standpoint.
Interesting.
And that's no big deal because it still works.
Wait, just a moment. So potentially something could be not well founded but still work.
So I don't really know. That's what I say. I mean, maybe it's well founded, maybe it's not. But I don't think it's captured by set theory. I think it's something different. And I'm not good at logic. And as a mathematician, you have to give up some. You cannot control everything in what you're doing. There are some aspects of mathematics that may be a bit too abstract for you, and you have to just basically accept that it just works.
Okay, let's rewind prior to category theory. Let's just pretend we're 100 years into the past. What I'm curious about with this question of how do we know when we found the correct axiomatic system is in physics, there are attempts to make axiomatic systems of physical systems like axiomatic quantum field theory or the Dirac von Neumann axioms of quantum mechanics or what have you. And then we test whether or not these are correct if they give us accurate predictions, if the model matches the data. And then we'll say if it doesn't, then our axioms are incorrect. Now, what's interesting is in math, let's imagine, so this is one idea of how it may work. We have a set of theorems. Let's enumerate them 1 to 500. Maybe 1 is the Pythagorean theorem, and number 500 is Fermat's last theorem, and number 250 is the intermediate value theorem, what have you. Okay, what are axioms that can tell me that all of these are true? Because I already have deemed them to be correct. Okay, so this is prior to the development of set theory, is what I'm saying.
So, there is an example of axiom having issues or not. Is the Euclid axiom, is it correct to assume the way it's been done for basically two millennia that, through a point that's outside a line, there is a single parallel going through it. Well, if you do plane geometry, that looks like it's true. So you want to take it as an axiom. But do you have to do it? So again, the two things are whether or not your system is consistent. If your system is not consistent, then you're in big trouble. You should throw away the axiomatic theory because it just doesn't work. It proves everything, including the contradiction of everything. But if it's not contradictory, if it's consistent, then it is a viable theory. The question is, what does it even mean? And you have an infinity of possible theory that you don't really know what they mean. So what happened with this axiom of having a single line going through an external point that is parallel to a line, that you can decide that it's false, and you can, and this is again the meaning making activity that comes in with. You can declare that you have 0 parallel going through that point, or you have an infinity of one of parallels, and in both cases, you have an interesting geometry, and you can interpret it as elliptic geometry or hyperbolic geometry, and it's actually very fruitful. So it's just describing something else that was not the intention of the people who wrote the original set of axioms, but it's actually very interesting. It's a different object. There is a general principle that says, that whenever you have a consistent set of axioms, well, it means something in a certain model. The question is what, and what are you going to do with it? So you can always extend. That's one aspect of that special mental game called mathematics, is you can always expand the mathematical reality by new things, as long as these things are not inconsistent. So, and in itself, you can view it as a very anti-Platonician mechanism, because basically anything that is formally correct can be made sense of if you find a way to make sense of it.
Okay, let me amend my question. Let me say it like, rather than there being 1 to 500 theorems, let me say 1 to 500 statements that we think to be true, because by saying the word theorem implies that you've already found a proof to it. But let's just say we believe these to be true. We have some foundational system. Maybe it's based on axioms, maybe it's not, but we have some way of proving, and we've convinced ourselves that these 500 are true. Now we're trying to find the consistent axiomatic system. So let's condition on consistent axiomatic systems, not just all. Now we're trying to find which one is the correct one for us as mathematicians to explore. Now, what I want to know is, I imagine that an axiomatic system, there's a case here. One that all 500, we found one. We found an axiomatic system that shows the proof of all 500, but it also shows a 501th statement that we believe to be false. Do we then say we're wrong as mathematicians and that the 501th one is correct? Or do we say we have not found the correct axiomatic system yet?
Okay, so it's a very tricky question, because we have to, there are some words that you're using that are not completely obvious to interpret. The word true is very difficult to interpret in what you're saying.
Let me just make it clear then. Okay, because some people would say the Banach-Tarski paradox is evidence that the axiom of choice should no longer be there because it produces the Banach-Tarski paradox, and we don't approve of this paradox. But you could also bite the bullet and say, sorry, there are some unintuitive results and you just have to accept it. So one is to say we're going to abandon the axiom of choice because it leads to something that we don't believe to be true. Maybe true. Again, you have some issues with true, and many people do. And so we can explore that. That's one route. Or the other route is we can say that, well, we're just cowards and that's actually the truth. The Banach-Tarski paradox is not a paradox at all. The Lowenheim-Skolem paradox is not a paradox. It's unintuitive, but you just have to accept it.
This is exactly the same story as the Euclid axiom. I think the Banach-Tarski paradox is exactly like the axiom that there is a single parallel. And it was shocking to people that it could be otherwise. And in a way, Banach-Tarski might be saying, like, maybe it's a hyperbolic geometry and you're not happy because that was against your intuition. But again, I did not mention the issue with truth as a way to dodge the question. I would say it was rather to focus on what's really important here, because we tend to think that formal logic is about truth, but formal logic is not about truth. Formal logic is about studying deduction systems and coming from a number of statements that you suppose you know and getting to other statements. So in your example, do we have a bunch of results that we believe to be true? And if we believe the 500 of them to be true, can we find an axiom system? Yeah, just take the 500 results that you believe are true and make that your axiom system.
Mm-hmm. Okay.
Two things can occur. It can be inconsistent. In that case, you're in trouble because you're asking for something impossible. You cannot have these 500 things being true together in the way you want. So you were wrong. But usually it's not supposed to happen. But then you have that 501 theorem that surprises you because you were expecting something else to be true. Okay. Now there is a question is, if you had taken, so let's say that your 501 theorem is Banach-Tarski, okay. And you get Banach-Tarski and you're not happy because you don't like it, okay. Does it follow from the 500 axiom you took where you have no choice, you have to accept it? Does it follow from another set of axioms that you try to find to get to those 500 theorem? But could you have taken another one, and would it have been okay? Maybe. And the way to answer that question would be to take the opposite of Banach-Tarski, to say that it's false, and to add it to your list of 500 and ask whether this is consistent. So basically, whenever you can take a bunch of results and make them work together, then you have a viable model of mathematics that you can function with. The question is, all the models basically, up to when you get to a certain degree of sophistication, of expressivity, they always contain weird things, Like you can say, I don't like Banach-Tarski, but would you like a violation of the axiom of choice? I don't really think you would like that either. So you have to accept that some things seem unintuitive. And seem unintuitive is a very important word. And now we're getting into psychology. And this is why you cannot get rid of psychology, because unintuitive is not a permanent status. I'm not an expert in the Banach-Tarski theorem, but I don't find it disturbing. To me, I do not. I would not be able to prove it like right now, because it's been a long time I thought about it. But last time I thought about it, it seemed okay. I didn't see any issue with that. Why? Because my intuition has been rewired by my practice of mathematics, and actually, I'm okay with it. I don't have any issue with that. I don't view it as a paradox.
Now, some mathematicians and computer scientists who I've spoken to on this show, and I won't name names, but some of them are finitists, meaning that they don't believe infinity should be a part of math. They find Gödel's incompleteness theorem to be, the first incompleteness theorem to be unsettling. And their route is to say that our axioms, that we're not supposed to capture all of piano arithmetic. It's just supposed to go up to some finite number, f. And yes, you have some potential infinity, but it's not an actual infinity. In those cases, it seems like what's happening is their axiomatic system proved something which they find so horrendous that they abandon the axioms. And it's unclear to me, when do we know that something that we're trying to capture with our intuition has been correctly captured by something explicit? So intuition's more fuzzy, and then we have something explicit. We're trying to capture this fuzziness. But sometimes when we do so, we betray the intuition. And we don't know, is it because our intuition was false, or is it because our axioms are false and our intuition is correct? We don't know which one to overturn, and I don't know how that decision is made in generality, not just in math, because this also applies to, let's just say, life. This is a standard example I think about. We can imagine that 1,000 years ago, or we can imagine 4,000 years ago, the word life, if it was around, referred to something like the sun was alive, you are alive, frogs are alive, plants are alive, but the dirt is not alive. And then we're told, well, life has something to do with variation, heritability, and differential fitness, and speciation. And then we say, well, yes, okay, by our definition of life, our explicit one now, you are alive, the frog is alive, the dirt is alive, because the dirt has some microbes in some sense, the sun is not alive. But the whole point of the definition of life was to capture what we meant. So in that case, we just said, well, we were wrong calling the sun alive. But it's unclear to me, when do we say that this explicit axioms or our explicit description is correct versus not correct?
So this question of correct or not correct, I think it's more relevant to the non-mathematical world. Because again, in mathematics, whenever it's consistent, you have an interesting theory to build. And I actually think that the people who just want to do finite constructive mathematics are doing great stuff. I love that kind of math. But on the other hand, the people who use infinity in ways, they prove theorems that are meaningful. So, and you could say that doing axiomatic set theory is just a finity theory of sentences expressed in the language of set theory, and it just happened that some people are happy with the meaning they project onto it. So in mathematics, you have that plurality of domains of research and objects you study and phenomena you can study. And it's why actually you don't have that phenomenon in mathematics of having schools where people say life is like that, and other people would say life is. Some people would say, for example, I think a while ago there were people disagreeing with the fact that humans were animals. Probably. I think it's becoming marginal, but it used to be like that. It's not like in mathematics. Some people are arguing that humans are animals and humans are not animals. It's that some people work in theories where humans are animals, and some people work in the other theory, and they prove things, and it's always interesting, and they can exchange and discuss, and they're happy to have different taste. It's a matter of taste. Now, in the real world, you have at issue at definitions, or what you describe as axioms is basically the definitions we're using. Have to be recalibrated from time to time, because we want to talk about that weird thing that is called reality, and we want to have some stable, and it just doesn't work. It's not really stable. So we have to recalibrate it from time to time. And it operates really differently. In mathematics, you don't recalibrate things. You say, okay, I'm going to do a slightly different theory. It's not going to replace the prior theory. It's going to say things that are a bit different, but I like them better. They kind of better describe what I want to express. But it's always additional. You never destroy anything you've done in the past. We can open a math book from 300 years ago and still we're happy to read it, maybe some bugs, but apart from that, it's okay.
This video is sponsored by Shortform. If you want a free trial and an exclusive $50 off their annual plan, then go to the link in my description, shortform.com/TOE. If you're like me, you've encountered books that are so dense, finishing them is actually just the beginning. Shortform helps with that. Their book guides go far beyond pastiche summaries. They critique, they add context, they include interactive exercises, and connect ideas across authors. Take Gödel Escher Bach or The Master and His Emissary, two of the most demanding reads in consciousness studies on the popular market. My method is I read the guide first, then the book, then I read the guide again. So it's a triptych of engagement that cements better understanding for me. The GEB guide maps recursive structures in a way that exhibits intellectual pleiotropy, where one insight branches into consciousness, computation, and self-reference simultaneously. Shortform covers philosophy, science, and psychology, ipso facto, the intellectual core of this channel. They publish new guides weekly, and subscribers vote on what books get covered next. Their browser extension, Shortform AI, summarizes articles and YouTube videos with a single click. Go to shortform.com/TOE for a free trial and an exclusive $50 off your annual subscription. That's shortform.com/TOE. What is the difference between the math that, say, Lean is doing, a formal system, a program, seems to be doing math, and a mathematician? Which one is actually doing math?
I think the mathematician who is using Lean to do math is actually doing math. Lean is, I'm pro Lean. I'm not against Lean. I think it's a great idea, and there are serious issues with the way mathematics is written and done. These issues come from real problems that people are not doing it on purpose the wrong way. When you write a math paper, you're trying to express something. And you're trying to prove a theorem. You're not trying to prove a theorem to a machine. You're trying to prove a theorem that will be accepted as a theorem by your fellow mathematicians. And you do that not by producing what is the official definition of a proof, that is a sequence of derivation within an axiomatic. So, these things only exist in the dictionary. It's only in the dictionary that people pretend that mathematics is a game of formal deduction. When you write an actual math paper, it's not what you're doing. You're basically waving hands. You're explaining in a kind of hybrid language that is blending some plain language phrases and sentences and some formulas that are more or less rigorously defined. most of the time the definitions are correct. The definitions are the most important part because these are this is the only solid ground you find in math papers is the definitions. Many mathematicians will tell you that they look at the definitions and the proofs, that's another story for proofs. But the definitions and the core statements should be at least rigorously done. Now, if you do that because if you were to write an actual formal derivation, it would take possibly, I don't know, possibly millions of pages if you were doing that in the actual Zermelo-Fraenkel framework. And nobody actually does that. And there is an example of that, which is how Russell and Whitehead prove that 1 + 1 is equal to 2. That comes after hundreds of pages. So if you just want to prove the basic results, you need hundreds of pages. Just imagine if you want to prove the classification of finite simple groups. Okay. So lean and that approach is to say that, okay, we may continue to write papers like that, but we should do the missing part, that is to make sure that the proof is actually a real proof in the sense of formal mathematics. So there is an effort to try to build the interface between the actual math publications and to offer some interface to a formal system where some proof assistant, because humans cannot really write them, but if you have correct UX, then possibly you can build a complete derivation of that. And I suspect this is how mathematics will be done in maybe, I don't know, I won't risk to propose an exact time frame, but I think we will get to that because there are issues with, papers are published and we not only are we're not really sure if they're 100% correct, but it also takes a lot of human effort to make sure that it's has a good chance of being correct. So this is very disruptive to the actual functioning of academia. I have a personal example of that. One of my papers took almost 7 years to get accepted, and that was horrible. That was just a nightmare. 3 referees gave up because the paper was too complicated, and it's for good reasons because it's difficult, but for bad reasons because I've been sloppy at places, which is what happens when you write a very long, difficult paper. And that's inhuman, to have to live with a refereeing process that takes 8 years and years.
Yes.
Because everybody was kind of agreeing that if the paper was correct, it should be published. But the question is, was it correct or not? So if there had been something like lean, and what I would dream to be the future of AI-assisted mathematics, that would be, a system that basically fills the dots, from the human proof to formalized proof, because this should be a pretty mechanical thing to do. Then I should have been able to press a button and say, okay, my paper is correct. I would have been very happy with that.
Okay, many threads. I'll pick on 2 of them. You mentioned definitions earlier, and a mathematician I was speaking to actually from the University of Toronto, right here, is Dror Barnett. And I asked him something like, what's your favorite proof? Which is just a standard question that many high schoolers have. The square root of 2 is irrational or something like that, whatever. He said, Kurt, what I find more interesting is definitions rather than proofs. We have an emphasis in undergrad for theorem proof, even in graduate studies, but as you do research, it's more, what are the right concepts? And he said he found that to be more interesting. He also said, and I want to hear your take on this, Dror also said that it didn't take 100 or 200 pages to prove 1 + 1 = 2. We didn't validate that 1 + 1 = 2. Instead, we validated that the axiomatic system was correct. Because had that axiomatic system produced something different, we would have thrown it out. But yet, it could have been a perfectly valid system in and of its own that aliens maybe want to investigate, and maybe it's consistent. Although, something I don't know about, and perhaps you know about, is there are different logics like pair-consistent logic. So I don't know if an axiomatic system producing an inconsistency actually breaks it from a formalist standpoint. But that's a whole other rabbit hole we can get to on another podcast. So anyhow, do you agree with Dror there that we often say, as popularizers of math, not science, popularizers of math, that it took 150 pages to actually prove 1 + 1 = 2. We say that, but isn't it more correct to say it took 150 pages to show that this formal system is consistent with what we know, and then that gives this formal system more credence?
Yeah, I think that's completely correct. It's not just about the formal system being correct, it's about it having the expressivity we want. And I think this is what they were trying to do. Trying to recover a result that people were previously agreeing on. Like nobody was disagreeing that 1 + 1 = 2. And I completely agree with him on proof are the technique used by mathematicians, but they're not the reason why they do mathematics. They do mathematics because of the meaning they project onto that. And meaning is about perceiving these things. I mean, I prefer to think of mathematical objects and to think about mathematical reasoning. I actually, when I was 17 or 18, I was happy with doing reasoning because I was maybe that was kind of new for me to be able to write down actual proof and that. And when I grew up as a mathematician, I started reasoning less and less and visualizing more and more. And to me, understanding something is about being able to relate, kind of visualize it. Visualize is not a good word because it doesn't have to be vision, but it's about feeling things.
Yes.
And my favorite things in mathematics are not proof, they are objects. So the definitions are the gateway to the objects. But just the fact that certain objects exist, I find it really beautiful. The fact that there is a monster in dimension 196,883 is beautiful. I mean, that this object is existing. And the proofs are the gateway, like the definition. They're gateways to creating mental representation. But the reason why we're doing that is to get this representation. It's like having a treadmill. I mean, nobody loves treadmills. People like to be in good shape. It's the same thing.
You and I met on Substack. I'll place a link to your Substack on screen over here. People can visit it. And I'll also place a link to mine in case people are interested as well. What many viewers may not know is that you had a permanent position at CRNS or CNRS, sorry, if I'm not
CNRS.
mistaken. Yes, you essentially, if I'm not mistaken, had tenure for life. So it wasn't that you couldn't get a job or something like that. Many people leave academia because they couldn't get a job. They go to industry. You left both industry and academia. Tell me about that. Tell me why.
So it's actually even worse than that. I have a tenured permanent for life research-only position, which is something that's absolutely crazy.
Right.
So basically, I had no teaching duties. I could have spent my life, doing whatever I wanted every day, and the pay was not great. So that was an incentive to go to not keep this one position permanently, but still, I had the option to keep it forever, and I quit, which is very unusual.
It's extremely unusual. It's unheard of. So there are very few people. Eric Hole is someone else who happens to be on Substack, who I'll be speaking to at some point as well, who was also on, I don't believe he was tenured, but he was on tenure track. And then he left that. He left academia. And it's so rare because there's prestige associated with academia. There's there's safety associated with a guarantee of a job. In your case, the people who have tenure most of the time, the one part of their job they dislike are the administrative tasks that they have to engage in, but you didn't have to teach, you didn't have to do all this miscellaneous auxiliary work. So what is going on with you?
So there are two sides to the question. One is what was my driver for doing that? And the second question is what made me brave enough to do it? And I will start by the second one because the second one is very anchored in a very specific moment of my life. When I was a PhD student, when I was 18, 19, 20, I was on a very fast track of going to elite math institution, learning very fast, progressing very fast. Then when I was 21, 22, I ran into very serious personal issues, and I had to quit studying for 2 years, and I abandoned my first attempt at doing a PhD in pure mathematics. So when I returned I restarted my PhD when I was 23 with a new advisor. And when I did that, it was very difficult for me. Very, very, very difficult, because my brain had basically stopped being able to do math for 2 years, and I had to relearn math. And that reinforced something that was always present for me in my interest in mathematics, is to view it not for the sake of doing mathematics, but for the sake of understanding what was going on in my brain. And I viewed my mathematical career as an experiment into, okay, how far can I push this thing? Can I really become a mathematician or not? That was an open question for me. I was very insecure back then. And so I did my PhD, then I had a 2-year temporary position in the US, and I was hired at CNRS, and I got that permanent position. But when I got my permanent position at the year I was turning 30, and I was still very insecure in my identity of, it's ridiculous, because in a way you have all the credentials you want. You're a pro mathematician from any external perspective, but internally I was feeling like I was a fraud, like many researchers do. I do think that actually people who do good research start feeling like they're frauds, because that's a very good incentive to work hard and try to do great things. Now, I quit mathematics at the moment, just right after proving a big theorem in my small domain. So it's a big theorem for me, but a small theorem at the grand scale of mathematics. But that was a fairly big one for me. And it resolved my inferiority complex. And I realized that from a pure ego perspective, I would not be getting much more by staying in mathematics. So it gave me the permission to be really sincere about what I wanted to do.
Interesting.
And I had just been giving that course. I discussed that course about the foundation of mathematics. So that was a very unusual course. I gave it at the École Normale Supérieure in Paris. That's very prestigious math institution, but I was not teaching the math students. I was teaching the humanities students. And that was an optional course that was basically it was a not-for-credit course. And I had a very small number of students who were brave and crazy, just trying to understand what is mathematics. They may have been heading to do a PhD in philosophy or stuff like that. And so I created that course that was a unique course of me trying to explain what is mathematics. And doing that, I realized that many of the things I had thought about mathematics were wrong. I had stopped interrogating the foundations of mathematics, because when you become a practitioner of mathematics, you basically, the stuff works. That's okay. You're okay with it. You continue. You just prove theorem. That's your job. But when you take a step back and you realize it doesn't make any sense, I thought it was a very profound thing, because, seriously, this thing, we're telling a story about mathematics, and we've been telling that story for literally over 2,000 years. And this story is meaningless when you look at it closely with honest eyes. We're used to the story, so we don't realize it's meaningless. But the story about Platonism and the story about formalism, the two of them are completely crazy when you look at them carefully. So I realized that there was this thing going on about the back and forth between formalism and intuition. And that was something that was taking place in my brain. And what happened to me from 17, when I started to study mathematics, until 35, when I decided I wanted to quit mathematics, is I transformed my brain in a very profound way. I became able to see things that, from my own perspective, seemed genius level. Not that my research compares to the actual geniuses doing that, but if I was, the theorem I proved right before quitting is theorem that was incomparable with what I was capable of doing when I was only 30. That I transformed my intuition, my cognition, in a way that was unthinkable to me within my prior system of thinking. So it changed everything I thought I knew about mathematics, cognition, our ability to grow. And I always knew that I wanted to tell the story to the general public. And I realized that this interest in not proving theorems, but about understanding how mathematics works, is a topic that is not taken very seriously. It's not something you're supposed to do as a full-time job when you're a mathematician. You're supposed to prove theorems. And I was feeling uncomfortable in that, having that research-only position, not really wanting to prove any theorems. I was exhausted because I had worked too hard proving theorems. And I wanted to do soft stuff, general public stuff. And I thought it was better to have a clean break from academia to do that.
You spend your days wrestling with the vicissitudes of consciousness, free will, and whether reality is a simulation, but some problems have elegantly simple solutions. Blue Chew Gold is the newest innovation from the #1 chewable ED brand, and gentlemen, this is a 4-in-1 tablet, which is setting the gold standard for performance. 2 ingredients for blood flow, plus apomorphine and oxytocin to amplify arousal and connection in both brain and body. It dissolves under your tongue and can work in as little as 15 minutes. Look, my wife didn't marry me for my humility. She married someone who optimizes everything. Everything. Some men settle for adequate. I find that philosophically unacceptable. Forget Netflix and chill. This is Netflix and fill. Make life easier by getting harder and discover your options at bluechew.com. We've got a special deal for our listeners. Get 10% off your first month of Blue Chew Gold with code TOE. That's promo code TOE, T-O-E. Visit bluechew.com for more details and important safety information. And I thank Blue Chew for sponsoring this podcast. If I'm understanding correctly, it was some insecurity that made you want to prove yourself intellectually, maybe to yourself and also to others. You could have gone into some other domain, maybe chess playing. And let's imagine you became the best in the world at chess. Then you would have realized, okay, this isn't what I thought it would be, or it does fill that hole. But now I get to examine, what do I actually want? Because the motivation for going into it was insecurity.
Yeah, I think I was a student of mathematics until I was 35. And then I was trying to understand what was mathematics and what were my capabilities. So part of that insecurity is social, and part of it was not really understanding the topic. And then at some point, because I'd made progress that was beyond doubt transformational for me, then I realized that, okay, what I've been conjecturing about the way it functions, conjecturing about the way my brain works, might actually be correct. So I might be onto something bigger. But this thing bigger is outside of mathematics. So it's maybe comparable to, you've been hired as in the founding team of a startup, and the startup becomes very successful, but it's not really your startup. It's not your business, not your idea. You might be successful in that, but there is this other idea that has been your idea from day one, but you did not really feel that you had the legitimacy to go into that direction. And then at some point you decide, okay, I'm going to leave this company. I'm going to start my own company. That's basically an idea like that. But the problem was I had no money. So the first thing I did is I took I took a break. So I took a suspension from my job. I was not crazy to quit formally from day one. I could take a temporary break for a couple of years. So I took a break. I found a job just, randomly, asking a friend who had a friend whose sister-in-law had a company. So I basically joined a company for 1 year. I made enough savings to have a personal runway of maybe 18 to 24 months. So it was the first time in my life that I actually had that kind of revenue. So I decided I would use that money to write the book I was dreaming of writing about mathematics. And I started doing that. And I did that for maybe 6 or 9 months. And then I realized I was not capable of doing that. And my money would run out before I completed the book. So then I decided to start a company because I was reading a lot about machine learning. So I decided to start a company just to finance my writing. So I thought it would keep me busy for 1 or 2 years, and it kept me busy for 12 years. I became basically founder and CEO of a MarTech startup using machine learning to apply to customer data, first-party customer data for B2C companies. So a very hands-on business, very concrete, very business-oriented.
I'm going to place a link to your book on screen. It was a hit in the French-speaking world, and it's been recently released into the English-speaking world, and so people can get their hands on that. Now, self-doubt, diffidence, this could lead someone to pursue math, but it can, for most people, prevent them from pursuing math or physics. They feel intimidated by it. There's some fear that's holding them back. What is your message to those people?
Wow, that's intimidating because, I know that these people are really suffering. And math is, in effect, putting a ceiling on the options of many people. The message would be, first of all, and it's a very important one, it's not hard-coded in your genome. There's a persistent belief that this is genetic. And of course, there is some genetic variability. I'm not a blank slateist person. I do acknowledge that there is some genetic diversity in human beings. And actually, some people are objectively cognitively impaired and they cannot do mathematics, let's say, high school level or whatever. But this is a minority of people. And the situation you're describing is about people who are otherwise intelligent. People who can read books, for example, people who can read my Substack. So if you can read my Substack, you're smart enough to do math. I'm 100% certain that your genetic makeup makes you capable of doing math. Now the thing is, it's a very special mental practice of things you do in your brain to do math. And if you've never practiced it, if you never found how to do it, it's hard to guess what's the right thing to do. But of course, if people tell you that this is genetic, you will not even try. So the core message is, yes, it's hard. Yes, it seems impossible because there's a certain practice that you need to learn that is invisible. That's something that you should do in your brain. But you can learn to do it. Of course, you will never get to the same level of people who started doing that when they were 2 or 3. But still, you can make stellar progress.
What's some concept, whether it's mathematical or physics or otherwise, some abstract concept, some equation or theorem that you struggled to wrap your mind around for, let's say, months, and then it clicked? What was that and what made it click?
So there's an interesting one. It's a technical one. It's a group cohomology and the bar construction in group cohomology. So these are things that were invented in the 1940s and 50s by Heilenberg and MacLane. It's basically to associate certain topological invariants associated with groups. So it's really pure math. But it's something I learned when I was in my early 20s, when I was, graduate students I was doing group theory, and I was supposed to know that stuff. That was really basic stuff in a way. And I never understood it. I mean, so what does it mean not understanding it? I could read the definition, I could read the construction, I could read the theorem, I could even apply it if needed, even though I never really applied because it didn't click. I did not really understand it. And I remember the very night I understood it when I was I think 33 or 34. I have to check the date, but I know exactly when it took place. It took place when I was actually working on proving the big theorem I was mentioning, which is actually in a way a theorem about group cohomology. So I was supposed to be a world expert in group cohomology in a way, but I still did not understand the basic definition of it. And one night I woke up and I realized that reinterpreting that thing that was defined using pretty terrestrial mathematics, reinterpreting that into very abstract stuff involving category theory again, made it trivial. And it's a very common phenomenon. There's many people who studied under Grothendieck were describing the fact that, he was starting to lecture saying, it was basically a stairway to going to the heavens, piling abstraction onto abstraction onto abstraction. At some point, you just realize that you're reaching the ground. And that's exactly what happened. Like piling as abstraction upon abstraction, realizing that group cohomology should be interpreted using groupoid covering, the universal cover of a group and the nerve of that as a category. And because the geometric realization of a nerve is a functor of two categories, then the bar construction is trivial. That was incredible. That was, that moment where this thing, you spend 10 years ashamed that you could not understand. And realizing that just increasing the temperature of your abstraction, making it like 100 times more abstract, made it 100 times more simple. That was an absolutely fabulous experience.
Now, this podcast is watched by researchers in math, yes, but also in physics and computer science. And then philosophy, there's also a large portion that are just lay people. So for those who are not mathematicians, who have no idea what you mean when you say nerves and functors, to explain, let alone cohomology, let alone group cohomology, explain it so that they could understand.
Wow, this is very difficult what you're asking, but I will try. So a group is the structure of symmetry of an object. When you have a triangle, you can have mirror symmetry by going through one vertex and the middle of the opposite edge. And you can also have rotation. So you have a dihedral group, that's the structure of that. When you have n marbles, you can permute them, you have a symmetric group. Basically, sorting things is a symmetric group. And basically, the thing about group cohomology is the core idea is how do you associate a space to a group? How do you go from having that thing that is very algebraic, that is the symmetries that you can compose, combine, multiply, that you have structure that with some kind of multiplication, like the Rubik's Cube is a group theory object. Everybody can, if you want to feel the complexity of a group, just take a Rubik's Cube. That's a good example. And how do you associate a space with a shape to a group? And the construction I was interested in was really about doing that. And now what's interesting is because when you have a space, then you have certain invariants that are called cohomological invariants, but the cohomology part is actually not the relevant one to what I'm talking about. It's really how do you go from a group to a space? And these things have been, this is really the central idea about, category theories. You have mathematical objects of different natures, and you can transport and reinterpret results about groups as results about spaces and vice versa. And you do that and you're happy because it illuminates your understanding, certain results about group that you can prove using the shapes of the spaces that you associate to them.
And you can't just assign spaces willy-nilly, so there must be some condition.
Yeah. And you want, of course, that to be functorial in a way that if you have a morphism between two groups, then you have a morphism between the two spaces. Of course, it has to preserve the structure.
David, why don't you tell me something that people misunderstand about you or misunderstand about what you're saying? That happens to everyone. Everyone's misunderstood at different points. But what I'm referring to is you're a public person, you've written a book, you have a Substack. there must be something that people say, David, yes, I understand what you're saying. You are saying X. But then you say, no, I'm not saying X, I'm saying Y. So what are you constantly misunderstood about?
So there's something that I find really annoying is people keep saying that I blame teachers for the poor situation about mathematics. And I actually don't blame teachers. I think they're victims of that. And people say that, it's people think that I'm making some social commentary about people's relationship with math. Actually, I'm making a statement about the nature of reality and the functioning of our cognition. And I think that we are making fundamental mistakes about human cognition. And everybody is trapped in those mistakes. And I'm trying to entangle that and trying to articulate non-absurd way of understanding what is going on in our brains. Not that I'm competent as a neuroscientist, but I just try to make sense of the actual practice of doing mathematics. And I'm always, I don't know how to react when I see, I've seen reviews of my book where people were saying, he's criticizing school and teachers. No, I'm not doing that. It's a much bigger issue than that.
When we spoke over email, I had to push our interview forward a week. And then you quipped, well, it doesn't make a difference. The foundations of math have been broken for 2,300 years. Another week is okay. And of course, that's a joke, but what did you mean by that?
Well, it's something embarrassing about what I'm trying to do. And every time I write an article on Substack and I have to press the publish button, I think, okay, why am I discussing these things? I mean, these are subjects for cranks, trying to discuss the foundation of mathematics and the nature of mathematical cognition and where those cognitive inequality come from. And the reason why I'm actually stepping into that ridiculous territory, I mean, you're not supposed to do that. You're supposed to talk about normal stuff, is because I do think we're seriously wrong. And it's a very bizarre feeling that, something that fundamental as mathematics is misdefined in a very profound way and has been for millennia. It's an embarrassing situation and we should get out of it. I'm very happy whenever I see that someone said the same thing before me, because that's reassuring to me. There is a short video interview of Ruben Hirsch. I'm a big fan of his 1979 article. I'm a bit disappointed by what he did after that. But about one of his books, there was an interview by the American Mathematical Society, and it's available on YouTube. And he's describing that situation. That is really a crazy situation. It's exactly the same one as what I had experienced giving that course to humanities students. He said that he was once teaching a course about the foundation of mathematics. And that was the first time he had a careful look at it as a professional mathematician. And he read about Russell and Hilbert and Brouwer and all their theories about, how mathematics was to be founded. And he realized that none of that made any sense. And he said, what can I tell to these poor students? I mean, what, Hilbert was wrong and Russell was wrong and Brouwer was wrong and we all mathematicians failed. And that's crazy emotions to have. You're not supposed to stumble upon bugs that big in our culture, but this is a very big one, very profound one.
What if someone says, okay, look, the fact that we have had incorrect ideas about the foundations of math for 2,300 years, actually, that's not a point in your favor. That's a point against trying to conceptualize math correctly. Because if we've been so off for 2,300 years, and yet we've produced Grothendieck and Terence Tao and Hilbert and so forth, and neural nets and etc., then that means that the foundations of math weren't terribly important to understand from a philosophical or cognitive standpoint anyhow.
So there's two different directions. Grothendieck did not need anyone to teach him mathematics in a way. And that's phenomenon that's very typical of mathematics. If you ask the top mathematicians, they will all tell you that, of course, yes, they learned very important thing at school, and they had this great teacher, or maybe this parent, or maybe this book they read that was very inspiring. But they also feel that there is something about their own mathematical practice that is something they learn by themselves. And I don't think that anything I've been writing can help produce new Ramanujans and new Grothendieck. I think they're generated by some random circumstances and very unique cognitive trajectories that cannot be produced by any advice, external advice. I think this thing materialized very early in infancy, and it has nothing to do with whatever I can say. But on the other hand, there's something that's really broken with math. I mean, if you think about the transformation that started 200 years ago, where primary school started to become something for everyone. That was not the case. 500 years ago, people were not learning to read. And then 200 years ago, gradually, country after country started to have a free, public, mandatory primary education. That's basically about two things: reading, writing, and mathematics. And that's interesting that we basically succeeded at doing that for reading and writing. Of course, there are some people who struggle with reading. It's not perfect, but people, on average, people have some fluency in reading and writing. And that's a big success. We could not have the world we have today if we had not achieved that. I mean, the digital life is a written life by many aspects. Yes, we have TikTok, but you still need to enter your password, So you still need to be able to read and write. Now, this other basic thing that is making people able to understand mathematics is a hit and miss. Well, yes, okay, people believe in numbers. They can manipulate even negative numbers that maybe 200 years ago were deemed too abstract for average people. We made some progress, but still, people seem to be blocked somewhere in their relationship with mathematics. And there is something fundamental that doesn't work, but we failed to onboard a massive chunk of the global population. And I do think it's a serious issue, actually. If you think about, the role, well, maybe AI, let's not go too much into that discussion about what AI can do and replace about our own cognitive ability, but we're living in a technological society where mathematics is at the foundation of basically every sophisticated object that we're manipulating. And some people are apparently handicapped. I don't think they're really handicapped, but for all practical matters, they are mathematically impaired. And that's a big issue. And I do think that, when we tell people mathematical objects, they exist in a parallel universe, I can see them. You don't see them? There's something wrong with you. How is it supposed to help them? There's something that is fundamentally broken with the idea that I know that many professional mathematicians are Platonists, and I think that they're misled when they say that. They want to say, yeah, I see them, I feel them, I want to believe that these objects are real. And this is an important step. I think it's what I call methodological Platonism. But it's very useful when you have someone who doesn't understand math at all to reassure this person that they're not missing a secret connection with these magical entities. It's just that right now they don't have an intuition for them. And mathematics is about building those intuitions. Now, it's something, you're transforming something that is magical into something that is tangible. It's a learning process. And there are certain things you can do in your head that will help you develop your own intuitions. And it's about your own neuroplasticity. And when you learn them, this will be obvious to you. Now, that's more interesting, that's more tangible, that's more practical. But if we refuse to reject the idea that Platonism is correct, then if we continue to be Platonicians, there's no way we're going to be guiding people into building their intuition.
Speaking of having some connection to a secret realm of a sort, or some obscure connection, the mathematician that shocks me the most of everyone that I've studied, even above physicists, above Einstein, above Hilbert, above Grothendieck, above Terry Tao even, is Ramanujan. There's something so odd about him. I haven't encountered anyone like him before or like him after. I don't know what the heck was going on there. He said that he would sometimes see formulas in dreams, and it had to do with gods or meditative practices. He had little formal training. And there's specific conjectured formulas. It's not like the primes are proportional in frequency to this and that. It's no, you take the derivative with respect to n of the square root of n minus 1 over 24 times the exponential. And these turned out to be true, many of them. What the heck is going on with Ramanujan?
This is incredible. Honestly, this is incredible to everyone. And just, he wrote like hundreds of thousands of formulas. You just take one of them and you look at it and you say, oh, is it possible that someone dreamed that? Now, you have to accept that he did produce them. He did, he was basically taking a piece of paper, writing down the formula, saying it's a theorem, and not being able to explain anything about a possible proof, about his thought process. Well, he explained some stuff. He said, okay, I was dreaming and then I saw blood flowing from the ceiling and I saw a hand writing the formula on the screen of blood and I just took notes. Okay. So let's accept that he really existed because he really existed. Now, what's the explanation? You have basically 3 ways of explaining that. And I'm going to tell you my preferred one.
Mm-hmm.
The first one is he was really inspired, as he was claiming, by his personal goddess. It's a mystical explanation. The second one is he was a mutant with superhuman capabilities that are absolutely miraculous, and his brain was a different machine from our brain. And the third one is something with his brain that enabled him to do that. Now, many people, and it's crazy to find that, many people reject the third explanation because they don't find it credible. But I find the first 2 personally hard to believe. I struggle to believe that he really had a personal goddess. That's not my way of looking at the world. Now, whether or not he was genetically different, he could be, exceptionally gifted from a genetic standpoint, but there's something wrong with it. If you look at genetic variability, we are all different. Like, let's say height. Height is massively genetic and it's proven. Okay, I don't know if it's 70 or 80%, but the variance is, in a country where there is enough food for everyone, the variance is mostly genetic. But we all have the same height. Exactly. Plus minus 20, 30%, but this is nearly exactly the same height. There's no difference of orders of magnitude. Look at running, 100-meter dash. Some people run faster, yeah. Usain Bolt ran 1.5% faster than the second one in the record-setting race, and 3% faster than the slowest person in that race. Men run faster than women, but the difference is about 10%. It's nothing. And when you look at Ramanujan, it looks like it's 1 million times better in terms of mathematical intuition than a regular mathematician. It's incommensurable. And the very nature of that points to something that is not genetic. You usually don't get that much variability within a given species. It's not like that. It looks like something that is produced by cognitive transformation and neuroplasticity. Let me give you another example. Playing the violin. I don't know if you play the violin, but I don't. If I take one, I will be incapable of doing anything with it. And if I know that if I train for 2 hours a day for the next 10 years, I would still be basically incapable of playing the violin. But I also know that it's not genetic, and some people learn how to play the violin if they start early. And of course, they look like a magician when you cannot play the violin. It looks impossible to do. And my feeling it's the same kind of learning, except that it takes place entirely within your brain. So this is, you could object that everything I'm saying is very arbitrary and very external to the actual formulas of Ramanujan, but I have a more concrete example to give you, which is if you take this perspective that he actually had a normal brain, but did very unusual things with his brain, then it opens an interesting mathematical question, which is, how did he do it? Like, is there a way to get to these formulas through thinking without making written computations? And I had, so when I was a student at the École Normale Supérieure, I had, as a first year student, we had a course by a mathematician named Xavier Viennot. And you can find videos of him on YouTube. And he has a website with all his files and all that. And the course was absolutely fabulous. He was basically constructing intuitive objects. Things like, dominoes, examinos, trees, forests, stacks, things, kind of combinatorial objects that you can play with. And he was explaining how to create a dictionary between certain constructions made with those very concrete, very intuitive objects and increasingly complex algebraic formulas. So this field is called enumerative combinatorics, but he was pushing it to the limit. And it was a full semester course, very dense, but at the end, we actually proved one formula by Ramanujan using completely visual objects. And it doesn't mean that he did it like that. You have, as always in mathematics, you have many different avenues to proving a theorem. But it proves that for this specific formula, but just one example, it is possible in a normal, maybe gifted, we were all gifted, but we were like maybe 30, 40 students in the room, and we all found it obvious at the end. That's a pretty strong phenomenon. It's possible for a brain of these 20-year-old students to find a visually obvious way of proving the theorem. So it's not just about ideology, about deciding whether it's nature or nurture or whatever. It's also about having a productive approach to removing mystification and trying to actually create things that were are made possible because you believe that it's not a magical stuff. So then you're going to find the solution. I think it's when you do mathematics, there are a lot of things that look like magic. Basically, everything has been proven that you don't understand looks like magic. But you have to say, okay, it's not magic. There must be a way to find it obvious. Because someone found it obvious. Otherwise, they would never have been able to prove it.
Yes, one of your most popular Substack posts is about how there's a Pareto distribution when it comes to what looks like talent, but we can just call it performance or something like that. And that's not explained by normal distribution of IQ. Again, we have to bracket Ramanujan because that, to me, looks like magic still, even hearing your explanation. So everyone else outside of Ramanujan, even if mathematical ability is normally distributed, and there's some evidence for that, but let's just assume even if that's the case, what you're saying is that ability is not the same as performance, and performance is something like ability times effort, times opportunity, times accumulated advantage.
I would say ability is a complex stuff. I mean, you have. I do think it's not just. It goes beyond performance. There's something about the when you do math, you have the feeling that some people are stronger than others. Okay, it's not a very well-defined notion, but you do have a feeling. When you speak with Terry Tao, you're scared to death because it's obviously much stronger than you are. Okay, Pierre Deligne is obviously stronger than than I am. I was working on related topics, and I spoke with him a couple of times, and I was very intimidated because he was so much smarter than I was. Now, this thing goes beyond the actual productivity. It's not about the number of papers they wrote. It's not about the theorem they proved. It's just about, you speak to them and they look at you and you see in their eye that they understand everything that you're saying. And then they're going to reply something to you that is exactly what you've been trying to find for the past 6 months and you could not find. And they just replied to you on the fly. This is mind-blowing. And so it's not quantified, but if you had to quantify it, so I was discussing with my friend Hugo Dumy-Copin, who got the Fields Medal a couple of years ago, and he was saying that he's in his own subjective, it's very subjective, his own subjective perception, Terry Tao was at least 10x faster than he was in terms of understanding new mathematical concepts. And a lot of the work of mathematicians is making sense of new stuff. So this uncalibrated subjective scale of being strong at math doesn't look like a Gaussian distribution. It looks like a Pareto distribution where you have orders of magnitude difference of wealth. It's not, Elon Musk is not like 2x richer than you are. He's, I don't know, many times richer than you are. It's incommensurable. We have a perception of people's strength in mathematics being distributed in the same kind of distribution as wealth. Now, that does not negate the fact that there is some genetic inequality between people that by default should be expected to be Gaussian. And it's one of the inputs to that, for sure. And there are many algorithms that can start from a Gaussian input and turn a Pareto distribution, but they tend to be noisy. And noise is the important thing. And now this is related to, of course, the experience of progress in mathematics, where it really feels like it's a capitalization process, where you stack abstractions on top of abstractions. And it's not just about doing it on paper, it's about doing it in your head, about using your prior abstraction as a scaffold to create new intuitions. So you build intuitions on top of intuitions. And when you do that over a sustained period of time, I'm talking about the practice of doing that, several hours a day, basically every day. Some people work on maybe not every day, but most days for 10, 20, 30, 40 years of your life. And what is the effect of doing that on your brain? Well, this looks like a capitalization process. And what's important in a capitalization process is that it's not fully deterministic. Because there are so many things, maybe you will have ups and downs in your life, maybe, and so on and so forth. So there's an interesting good news for everyone here, is for the very same reason why the gap is massive. It means, for the same reason, it means that you can make stellar progress. It's like with wealth, of course. Maybe you're poor, but if you find a better job and maybe start to manage your finances a bit better, you're not going to be absolutely wealthy, but you're going to run, go to a safer place in terms of your personal wealth. There's something like that about mathematics. You cannot become Terry Tao or Ramanujan if you decide today you cannot work so hard that you will get there. I don't believe that. But still, you can become maybe 10x or 100x or maybe 1000x better than you are. Because then maybe there's like 12 orders of magnitudes and maybe there's still 2 or 3 that are still accessible from where you are right now.
Terence Tao famously said that he has little understanding of topology, something like that. But then what's funny is that we then think, yeah, but your bar for what you consider to be understanding topology is far higher than most people. Most graduate students who take a few courses in topology would say, I have a grasp of topology. Terry Tao could probably write those textbooks and then still say, I don't understand topology. So what is understanding? What does it mean? You talked about it earlier when talking about your K-pi proof or the group cohomology.
Yeah, I have a very simple definition. really understanding something in mathematics is finding it obvious. You find obvious that 2 plus 2 is equal to 4. Your goal should be that things in mathematics should be that obvious to you. That's a very high bar. But the thing is, setting it like that forces you to ruminate until you actually manage to see them like that. And this process of, I did not understand group cohomology, even though I understood the definition, but it was like, it was like a stone coming from outer space. And I did not really realize why there was this stone that was having bizarre properties that was just in front of me. I could not understand where it was coming from.
Uh-huh.
And then one day, I found a way to find it obvious. It was a very abstract way, but still it was very obvious. And I still find it obvious. I remember, it's a trivial, it's just because the geometric realization of the nerve of a category is a functor of two categories, and you apply it to the universal
Cover groupoid?
cover groupoid. You do it's Galois theory for groupoids. It's trivial. I'm saying it in words. I'm sure that among your listeners, there's absolute nonsense to 99.99%, but maybe there are one or two guys listening to me saying, oh, wow, this makes a lot of sense. It's so obvious. It's like, riding a bike. Once you learn that, you cannot unlearn it. Good math that you really understand, successful math, is math that feels transparent to you. It's like riding a bike. You cannot unlearn it the same way you cannot unlearn 2 plus 2 equals 4. I have one more example of that. Something that you take for granted, that every kid in Western countries take for granted. You have a map or a piece of paper, and there is X and Y coordinates. Okay? This is crazy. Like, how could you unlearn that? That a point in a plane is defined by two coordinates, X and Y. Just imagine the kind of general lobotomy that would take place if we remove that from the things we find obvious. It's impossible to go back. The entire human race has accessed some kind of spiritual elevation where it's obvious to everyone that a point in a plane has X and Y coordinates. Now, go back 400 years ago. This is actually what Descartes invented. Before him, there were two separate fields of mathematics. There was plane geometry. It's about geometry, ruler and
Compass.
And compass. And there was algebra, formulas, numbers, equations, and they were not talking to each other. He just found a cognitive bridge between these two things. Actually, it's first example of category theorem. You have back and forth between algebra and geometry, but that's another story. You transform the entire human civilization by connecting two things that were unrelated before. And after you did it, it feels so obvious that people, they don't even think it's advanced math, but it was cutting edge 400 years ago. And this is another argument against the hereditarian case about mathematics. I mean, look, this was like hardcore research 400 years ago. Now it's obvious to everyone. We did not mutate that much in the past 400 years to turn something that is cutting edge into something that is obvious to everyone. So there is some global elevation of mathematical cognition. And it doesn't require any thinking to you to just think that, you have X and Y. It's just obvious. And this is what you want. This is the way you should understand math.
Now, speaking of obvious, when you were giving a seminar and Sarah was there, Sarah said, I didn't understand anything you said, or something like that. So it wasn't obvious to him. What changed about how you present? What occurred in your mind after that?
So it's an incredible story. I mean, that was one of the weakest math talks I ever gave because I wanted to prove a theorem back then, but I could not really prove it. So instead of having a talk where I was presenting some big fancy new theorem, I was just kind of reviewing the basics of the things I'd been working on for years, making them very easy. And there was Sarah sitting there at the front, looking at me for the whole talk for 90 minutes. It's a very long time. And then at the end, he walked and said to me, "You're going to have to repeat everything to explain that to me because I did not understand a word." And to be honest, he was right. I think after that, I realized that my talk was crap. Not because I had given a bad talk, but because there were miracles. So my talk was rigorous, but it was miraculous in many ways. There were things that were occurring that I could not really explain why they were working. And it's actually related to the stuff that later enabled me to prove the big theorem I mentioned. So he was spotting not a logical flow in my argument, but some intuition gap. There are things that, were not quite right. They should not be like that. There was some missing ingredient in my description. Now, what I found interesting is not just his criticism of my own talk, but the way he did it. Like, I thought, how can you dare to do that? It's not just that it's rude in a way, it's that he's exposing himself to saying, I don't understand a word. Why is he doing that? So my first reaction was to think, okay, you can afford to do that when you receive the Fields Medal at 27 and you became the first person to receive the Abel Prize. And of course, you can say, there's just provocation, he does whatever he wants. But then I thought, maybe the fact that he's doing that helped him become the mathematician he is. And I realized that I was not capable of doing that, not because I was not smart enough. Obviously, you don't need to be smart to say that, but because I was not brave enough or I was not secure enough to expose the fact that I did not understand anything. So I tried to replicate the technique to see what happened. So when you go to a math conference, usually you're in a small group of maybe 40, 50 people coming from all over the world, working on your domain. But within your domain, there are like subdomains and tiny subdomains. So maybe when you have sitting at the dinner, because it's, these conferences, usually they last 1 week. It's a very remote place and you just live together for 1 week. And at dinner, you're sitting maybe with a grad student or maybe with a postdoc, and you discuss, okay, what are you working on? And that person will start to explain something to you. And usually you don't understand a word because it's not, these objects they're mentioning are not objects you're working on every day. Maybe you learned about that a long time ago and maybe you did not really understand like the group cohomology thing. Like you're supposed to know it, but you don't really know it, which is a very embarrassing situation because when you're a pro mathematician, you're supposed to know stuff. You're not supposed to not know stuff. So maybe you ask a couple of questions and you don't understand the replies. And after that, you just shut up and you change the topic. You just discuss about something and you make jokes. People end up making jokes and, discussing anything but mathematics. Now, what I did after Serre did that very provocative thing is I tried to replicate that. So I was discussing at a conference with a guy, and I asked him what he was working on, and he explained, and I did not understand. And I took him apart and said, "Okay, please explain to me. Start, my brain is damaged. That's what I told him. I have brain damage, and I have attention deficit disorder. It was a private one-on-one conversation, so I know that it's not fun to play with these expressions when you're making public statements, but I'm just relating a private conversation I had with that guy a long time. And he smiled when I said that, and I just assumed that, I cannot focus my attention for more than 20 seconds, and please explain in a very simple way. And what I realized is that this created two subtle but very important changes in the dynamics of a relationship. The first thing is I had given myself an excuse to ask all the questions I wanted. Because the premise is I'm stupid, I'm slow. And if I declare that up front, then I will not be embarrassed. Because usually when you don't say that, you ask a question, but then you don't understand the answer. And that's very embarrassing. And then maybe you ask a second time and you still don't understand it, and that's even more embarrassing, and then you stop. But if you say, my brain doesn't function, please help me, then it's fun, and you can ask as many stupid questions as you want. And this is what it created for me. But the other thing it created is it changed his own attitude. It's basically when you're in a foreign country and you walk in a restaurant, they serve you the tourist menu because they think this is what you want.
Okay.
And this guy, so I had something with my memories because I wrote down that story. It kind of interfaces with my memory. So I think he was a postdoc or a grad student, but I'm not entirely sure because once I written it in my book, I can forget the details. But you see, my brain is not working so fine. But this person had in that kind of implicit pecking order of mathematician, he had lower status than mine because I was a permanent CNRS researcher, which is a fairly prestigious position. So until then, he was serving me the tourist menu. He was trying to look impressive. So he was explaining things by the book and not by the easy book, by the really, look how impressive I am doing this kind of very abstract mathematics. And after I told him my brain was damaged, then he shifted. He served me the menu for the locals, the menu for himself. I was asking for not how he was talking about his research topic for a research proposal where it has to look very important and glamorous and all that. I was asking for the way he was making sense of it for himself. And he was very happy to serve me that menu because that was much more personal, much more intimate, and much more simple. Of course, he was starting from very basic examples. And I realized that there was something magical in this tactic of pretending you're very naive and you ask stupid questions. Interestingly, years later, when I'd become a startup founder and CEO, once I was in Silicon Valley and I was discussing with some guy who was a pretty high VP at a very big software company. And he was someone I was having regular discussions with, but it struck me that once he asked me for something about machine learning, about the way we were doing machine learning in our company, and I started to explain things in a very conceptual way. And he said, stop. Excuse me, but I'm going to ask a stupid question because that's the way I understand it. And it struck me that it's the same exact pattern, the one I noticed with top mathematicians.
Super interesting. Okay, so now let's assume some younger mathematicians are watching. Okay, and they've heard this story, but they want to know how can they apply it for them. Yes, there is the specific tactic of admitting ignorance or playing dumb, which may or may not be playing, but doesn't make a difference. Okay, so they're watching. So they heard Sarah speak to you. Sarah confesses his ignorance or his lack of understanding, but there's a hierarchy there. There's a dynamic. Now you to that other person, you could afford to say, look, I'm not understanding. I have ADHD, blah, blah, blah. I have brain damage. You get the idea. You can afford to say that because of the dynamic. Now, there must be a productive way to say you don't understand. You gave the example where you were at a bar and then you say, look, I don't understand this. And then the person explains it. Then you say, I still don't understand. Person explains it. And then at some point you just give up. What is the answer? To not give up? What is to ask differently or to confess foolishness? What is it?
So, first of all, I'm describing reality. I'm not necessarily having solutions for everyone on every single day. But what it says is there are social feedback loops that will amplify. And that's, when you look at a Pareto distribution, it must have feedback loops. Otherwise, you don't get Pareto distributions. So I just mentioned an explicit feedback loop that is a social one. First of all, at some point, if you persist, if you make progress, some of these natural, easy feedback loops will activate. But probably you're not there yet. So message one is, be patient, things will get better. Your rate of making progress in mathematics will actually increase over time. The second practical advice is, clearly you cannot go to Jean-Pierre Serre and ask him to repeat 10 times the answer to a stupid question. It will not work. You cannot afford to do that. So maybe just find someone you can speak with. And I do think that peer learning is super useful in mathematics. If you look at how mathematicians learn stuff, they learn stuff at the blackboard. But what do they do at the blackboard? Just usually 2 or 3 people speaking, each with a piece of chalk and trying to make sense of something that is too hard for each of them. But with this back and forth, being very naive, being very open, you can make progress. And I do recommend to all students of mathematics to find the right peers, people who are not here to look up, to look down on you. Sorry, to look down on you, and they actually are willing to be at your level and accept that you're their peer, and the 2 of you will make progress together. I think it's the best way to navigate mathematical studies. When I was a PhD student, in my second attempt, my finally successful attempt at doing a PhD in pure mathematics, I was very shy, very insecure, and I could not really speak with my advisor because I was too scared. But there was this prior student who was still in the same research team, was a bit older than me and much more advanced. And with him, I felt comfortable asking stupid questions. And he was very kind. He was very nice. Maybe if the person next door is an actual asshole and you should not do that. I don't know. But try to look for someone with whom you can have that relationship.
I recall you said, and it could be in your book, I don't recall the source, but you said that textbooks are meant to more be like reference manuals than primary sources, and that peer-to-peer, when a mathematician or someone is teaching something to someone else, they're often teaching these implicit metacognitive tools about how to think about this and that.
Exactly. And it's beyond that. It's also dynamic in the sense that when you understand something, you find it obvious. And when you find it obvious, usually you have many angles to look at it. So if we were to continue the conversation, and if you were a mathematician and we were to continue the conversation about the thing I said about group cohomology, which I said in a very provocative, short way that nearly nobody in the room could understand. Okay? But if we were to continue, I would not know how to continue if you did not share with me what you already understand and what you don't understand. And then, because this thing that is now obvious to me, it has many facets, and I can choose the right angle depending on what you're telling me. So there's a back and forth. And this is one-on-one discussion is not just that it's more informal, it's that it's more personalized. And great mathematical teaching is personalized. You can go 1,000,000 times faster when you personalize it.
Right. Okay, so suppose you're lost and you say, save me. You can't have someone save you unless they know the general location where you are.
Yeah, I need to give you my hand, but where are you? So you need to scream in the dark, and I will try to find you.
Right.
And this is really about that. So if you do that, you can. And interestingly, there's another phenomenon, which is, and I experience that with my kids. I have two boys. One is 6, and the other one is 2. The one who is 6, I have some experience now. I've had some experience now teaching him mathematics, but in a very casual way, never formal, just trying casually to discuss things. And what I realized when I discussed with him is, maybe I started out with the idea that I would teach him concept A or result B.
Mm-hmm.
But maybe after adjusting for where he's actually situated, that's concept C that I will teach him. And I will never get to concept A because that's not the right one for him. And very often when you start a conversation with someone trying to explain some, let's say you want me to explain why the bar construction is trivial if you look at it as in terms of functor of 2 categories. Maybe I will just have to explain to you what is a category and what is a functor. And maybe that would take the full hour. And that's fine because you will have made progress. What is really important is not to get stuck where you are, is to make progress. And maybe it will be for our next conversation that we will explain the theorem. And you have to be very practical, very humble about about what you're going to learn. When I discussed with that guy at the conference where he was explaining me his research topic, he actually never reached the actual moment where he was discussing what was his actual contribution to mathematics. He just explained to me some preliminaries that I should have learned when I was a graduate student and I never understood. But it was fine. I was happy when I exited the conversation. So there's so much to it's like, you can have Usain Bolt as a coach. He will not make you run the same speed, but maybe you will run faster than you were running before he coached you. That's what you want. You want people to be happy and make progress. That's a very, very humble but universal situation.
Okay. So the lesson that I'm taking from this is that it's often said that the teacher needs to meet the student where they are. And that's true. But here, because I was asking you to give advice to the mathematicians and the researchers who are watching, it's also your responsibility, if you truly want to make progress, to let the teacher know where you are, to not pretend you're in some place that you're not.
Yeah. And you should not have exaggerated ambitions in terms of understanding. And a really good math teacher is someone who meets you where you are and makes you. Many mathematicians think of mathematics as rock climbing. It's a very common metaphor. It really expresses something. Maybe you cannot climb that wall right now, but you can climb the smaller one. And a very good math teacher should be very honest about that. You mentioned Joel Biden saying that his favorite proof is the proof of square root of 2 being irrational. I know why he says that.
No, I was just saying that's an example of a common.
Okay. Oh, okay. But for me, it's my favorite proof. Because this is a proof where I can explain what a proof is. And I can explain that to a child. And that's fine. You just explain what is a proof. And you explain something fundamental to someone, but it's very naive. It's very simple. I cannot explain how the proof of a very complex theorem works, but I can explain how this one works to everyone.
So you could request your friend to provide you more and more information. But here, suppose someone was to come to you and say, teach me about the bar construction. You say, okay, in order to do that, I have to teach you about a functor. In order to do that, I have to teach you about categories, which requires an entire framework. Category theory, the introduction of, may take an hour, 2 hours. I imagine someone would feel like, I'm just going to waste your time. Why don't you just tell me the topics that I need as a prerequisite, and then I'll go and learn that on my own. So what's your answer to that?
So there are two things. You want to understand how the toaster is working, or the inner workings of the toaster, or you want to understand how to use the toaster. So another important thing is most of the time when someone comes up with a question is because they're stuck somewhere. They want to prove a theorem, but in the theorem they need to use some technology somewhere and they don't know how to use the technology. So here you just keep it simple. You say, okay, no. Let me show you. This is where you put the bread. This is the button you press, and after 2 minutes, you're done. So you just explain the interface of the theorem. And then maybe, because it's a bit frustrating, you say a few make a few hand-waving remarks about how it works internally, but you're not really serious. Now, if the question is, how does group cohomology really works? Why is this construction working? Then you go to the other direction. It's really two different demands. You have to accept. Well, some people don't accept. I don't think that someone like Grothendieck ever accepted being presented with a technology that he did not understand. And that's a very unique and very powerful approach to being a mathematician, to reject everything you don't understand. But there are other people who are very happy to manipulate notions they don't fully understand, and they can leap through entire territories very fast. They're basically standing on the shoulders of giants and being happy with it. What's really important is to understand the human ask that someone coming to you with a question, and it can be very different depending on the context and what they're trying to do.
I have a question about hand waving. So suppose we went back 1,000 years and then picture proofs were accepted. Now we would say that there's something hand wavy about that, meaning unrigorous or gestural or notional. And then someone would say, well, the way that we thought of continuity was hand wavy, but the rigorous is epsilon delta. But then we'd say when you take a real analysis course or you take a certain real analysis course, like the one at the University of Toronto, it's called MAT 157. It's my favorite course, actually. They make you painstakingly prove with modus ponens every single line of certain proofs. And then you'd say, okay, well, that was the truly rigorous one. But then you can imagine someone saying, no, not even, that's not even true rigor. Lean, putting it into lean and getting a computer to say it's true is the true rigor. Do you think we'll ever get more rigorous than that? Do you think we've bottomed out at the most rigor right there?
I'm not sure. And again, my definition of mathematics is that it's this back and forth process between understanding and formalizing what we understand. And there's a never-ending back and forth. And in a way, Russell and Whitehead reprove that 1 + 1 = 2 in a very different way. So you could say that they tested the equation, but they also consolidated it in a different way. So there are, but it doesn't mean that it's going to be productive to always question the rigor of stuff. I think you should have a good reason to question it. And you mentioned that 2,000 years ago some picture proof were accepted. Well, if you read some actual papers by Thurston, it looks like they're still accepted today. And that's fine because there's some stuff that is easily drawn but very hard to prove. I have in one of our papers, I have a lemma where I give a proof that is one picture, and the text says a picture is worth 1,000 words, and that's all. End of proof.
Interesting.
It was accepted. It was published.
David, what's the most inspirational advice you've received?
Oh, it's a very practical one from my PhD advisor. When I was so I was at Yale, I had that very nice temporary 2-year position, and I had proven the theorem that was not very hard, not very profound, but I had found a way to write the paper in a way that, it's like when you write a good piece where you found a good angle that makes it very sexy. But it was not very profound in a way, but it was referring to questions that were asked by fancy papers. So I was thinking about, submitting it to a very good journal, but I was not sure whether it would get accepted. And he said, go for it. I don't know. Maybe not. It's not clear. There's pros and cons. I don't know, but don't self-censor yourself. You will see. And that was the first time I accepted taking some risk from my ego, because usually until then I was very careful. I was so insecure that I was careful because I was afraid of being rejected, or of people saying your paper is crap, you're going to reject it. So that's difficult. And I submitted it, and it was accepted very quickly. I got that permanent CNRS job thanks to the paper.
Mm-hmm.
And the lesson was, if I don't fail often enough, it's because I'm not trying hard enough, and I should do things even if I'm not sure they're going to work. And that was very helpful for the rest of my life.
I very much like that. There's some percentage you can put to it, that if you're not failing 10% of the time, then it means you're not trying hard enough. But anyhow, thank you. Thank you for spending so long with me.
Thanks a lot. That was a wonderful conversation. It was very interesting. So I know your style, and I know that you have this thing about being very patient, about asking the tricky questions and spending the time on them. So I played the game. I hope you're happy with the result.
Hi there, Kurt here. If you'd like more content from Theories of Everything and the very best listening experience, then be sure to check out my Substack at kurtjaimungal.org. Some of the top perks are that every week you get brand new episodes ahead of time. You also get bonus written content exclusively for our members. That's kurtjaimungal.org. You can also just search my name and the word Substack on Google. Since I started that Substack, it somehow already became number 2 in the science category. Now, Substack, for those who are unfamiliar, is like a newsletter, one that's beautifully formatted. There's zero spam. This is the best place to follow the content of this channel that isn't anywhere else. It's not on YouTube. It's not on Patreon. It's exclusive to the Substack. It's free. There are ways for you to support me on Substack if you want, and you'll get special bonuses if you do. Several people ask me, like, hey, Kurt, you've spoken to so many people in the fields of theoretical physics, of philosophy, of consciousness. What are your thoughts, man? Well, while I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. And it's the perfect way to support me directly. kurtjaimungal.org or search Kurt Jaimungal Substack on Google. Oh, and I've received several messages, emails, and comments from professors and researchers saying that they recommend Theories of Everything to their students. That's fantastic. If you're a professor or a lecturer or what have you, and there's a particular standout episode that students can benefit from, or your friends, please do share. And of course, a huge thank you to our advertising sponsor, The Economist. Visit economist.com/toe, TOE, to get a massive discount on their annual subscription. I subscribe to The Economist, and you'll love it as well. Toe is actually the only podcast that they currently partner with, so it's a huge honor for me, and for you, you're getting an exclusive discount. That's economist.com/toe, TOE. And finally, you should know this podcast is on iTunes, it's on Spotify, it's on all the audio platforms. All you have to do is type in Theories of Everything and you'll find it. I know my last name is complicated, so maybe you don't want to type in Jaimungal, but you can type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comment that Toe listeners also gain from replaying. So how about instead you re-listen on one of those platforms like iTunes, Spotify, Google Podcasts, whatever podcast catcher you use, I'm there with you. Thank you for listening.